Hello everybody. Today we are going to learn a few important things in Boolean algebra. I have already sent you all the Boolean laws that you need to remember in order to follow this lesson. So I will advise that you go through the laws once more and keep them ready in front of you whenever you are solving these kinds of algebraic proof in Boolean algebra. Today we are going to study De Morgan's law. As you all know, that De Morgan's law, there are two laws to it. The first law says that the complement of the sum of two variables is equal to the product of the individual complements, and the other one is obviously the dual of this, that is the complement of product of two Boolean variables is equals to the sum of their individual complements. This is De Morgan's law. Now what is usually asked for is proving Boolean laws either through truth table or through algebraic method. Other laws are quite simple to prove through truth tables. De Morgan's law is also very easy if you are asked to do it using truth tables, but when you are asked to prove De Morgan's law, either first law or second law, then through algebraic method, then you have to follow some specific method. We are going to discuss that now. Now suppose we have to prove the first law, De Morgan's first law. Now, as you can see the first law, in order to prove this, we need to prove two things. Now, this is the complement of this. So, as you know that for any variables or any propositional variables or Boolean variables, the product of the variable with its complement is always 0, and the sum of the variable and its complement is always 1. So we have to prove the same thing over here. Here in this case I am considering a plus b as x and a dashed dot b dashed as x dashed. So here x is equals to a plus b if we follow this, and x dashed according to De Morgan's law they are saying it is this. You have to prove it. So what you need to prove is actually two things. One is that a plus b, that is we are considering this one, a plus b dot a dashed dot b dashed is equals to 0, and you also need to prove that a plus b, I will do it over here. You also need to prove that a plus b plus a dashed dot b dashed is equals to 1. If you can prove both these equations, then you can say that you have proved De Morgan's first law. If we take this equation and apply distribution law to it, then you will get a dot a dashed dot b dashed plus b dot a dashed dot b dashed. This is the LHS of this equation. So a into a dashed is 0, so this term becomes 0, and again see b into b dashed is also 0, so this term also becomes 0. So you get a 0 at the end, which is equals to the RHS. So this equation, this condition is proved. Let's prove this condition. In order to prove this condition, what we will again apply distribution law over here. We have a plus b plus a dashed plus a plus b plus b dashed. This is again the LHS. Okay, now a plus a dashed is equals to 1. So this is 1 plus b. What am I using here? That a plus a dashed is equals to 1. That is actually this one. So this plus this is 1, 1 plus b. And over here again b plus b dashed is 1. So this is again 1 plus a. And we know that 1 plus any variable is equals to 1. So this is also 1 and this is also 1. So you prove that the sum of this and its complement is 1. So this side is also proved. This is equals to RHS, hence proved. Now since we have been able to prove both the conditions A and B, that means we have proved the first law. Hence De Morgan's first law proved. Now let's move on to the second law. Now we will prove the second law. The second law states that the complement of the product of two variables is equal to the sum of the individual complements. So again, if we take x is equals to AB, and according to the De Morgan's law, x dashed should be a dashed plus b dashed. So this is x dashed. So we have to prove two conditions, that is x plus x dashed is equals to 1 and x dot x dashed is equals to 0. So let us prove the first condition, that x is a dot b, that is AB, plus a dashed plus b dashed equals should be 1. So let's start with the LHS. So again, using distribution law, what we can say that if, okay, I will write it the other way around, that will be more easy to look at. So distribution law says that this plus this, that is a dashed plus b dashed, plus a dot a dashed plus b dashed plus b. Now we know that a plus a dashed is 1, so 1 plus b dashed. Again b plus b dashed is 1, so we have 1 plus a dashed. We know that 1 plus x is equals to 1, so this is 1 into 1, which is 1. So it's the first condition proved, which is equals to RHS. Let's prove the second condition, which should be that the product should be 0. That is AB dot a dashed plus b dashed should be 0. So again we'll apply distribution law, AB dot a dashed plus AB dot b dashed. This is the LHS. Now a into a dashed is 0, so this term becomes 0. Again b into b dashed is 0, so this term also becomes 0. So we get 0, which is equals to the RHS. So both the conditions are proved, hence De Morgan's second law proved. Now using De Morgan's law, you might be asked to find complement of some Boolean expressions. Let's do a few examples. Find the complement of x y dashed plus x dashed y. They will give you the question in this way. So f dashed will be x y dashed plus x dashed y whole dashed. Now if we apply De Morgan's law, you can see this as one term and this another term. So this you can see as a, and this you can see as b, so a plus b whole dashed. Okay, a plus b whole dashed will be, that means you're using first law, a dashed into b dashed. So here a is x y dashed, so it should be x y dashed whole dashed dot x dashed y whole dashed. Now again, if you see these two individual terms, this is again, we can use the second law. See, it is product of two terms, two variables, and the complement of that, that is a dot b, which is equals to then a dashed plus b dashed. So here x dashed plus y double dashed dot, this is x double dashed plus y. So now the double complement of any variable is the complement itself, so that means x double dashed is equals to x. So this will be x dashed plus y dot x plus y. This is the complement. Now there are many things to notice over here. You must observe that how we are breaking it. There is a very easy, simple way that usually students resort to learn how to do this, is that a plus b whole dashed is break the sign and make the two complements. Just break the line, change the sign. Okay, so we are breaking this line, this plus is becoming dot and this is becoming a dashed b dashed. So we are changing plus to dot and dot to plus, and x to x dashed to x, and whatever variable is there. See, again, if you see a dot b whole dashed, a will become a dashed, dot will become plus, b will become b dashed. Okay, see here also the original expression f was x y dashed plus x dashed y, and complement that we have found is x dashed, this is dot plus complement of y dashed is y. Again this plus has become dot, again x dashed has become x, here dot has become plus and y has become y dashed. So then you must be thinking that if we can directly find the complement of any expression in this way, then why do we go through all these steps? Because it is always not that the complement is so easy to found. Usually when the terms and the expressions are in the canonical form, you can do it in this way. Otherwise the answer should be something else. Let us see an example of such a kind of attitude. Let's do another example. Find the complement of f equals to ab dashed plus c dot d dashed plus e. So f dashed will be ab dashed plus c dot d dashed plus e whole dashed. So over here I can see this expression as a sum of two terms, where the first term x equals to ab dashed plus c dot d dashed, and the second term is e. So I will use the first law, that x plus y whole dashed is x dash dot y dashed. So let's put it here, ab dashed plus c dot d whole dashed dot e dashed. Again, if you look at this expression, this is again product of two terms, where again x equals to ab dashed plus c and y equals to d. So x dot y whole dashed can be written as x dashed plus y dashed. So let's put it here, it's ab dashed plus c whole dashed plus D double dashed means D. This whole thing to E. I'm not writing the double dashed. Okay, let me write. The next step I will eliminate that. That is AB dashed plus C whole dashed plus D dot E dashed. Now again this term is a sum of two terms, isn't it? And a sum of two terms. So where I can take x equals to AB dashed plus C, AB dashed and y is C. So again I will use here, it is a sum. I will x plus y whole dashed will be written as x dashed plus y dashed. So this will be A dashed plus B dot C dashed plus D dot E dashed. Now if you see in this equation, I can take this to be x, this to be y, and if I take this as z, what do I see? I see x dot y plus z. So can't I use distribution law over here? So I will be using distribution law. Which law? The second one. That is x dot y plus z is equals to x plus z dot y plus z. So that is A dashed plus B plus D, and this is C dashed plus D dot E dashed. So this is the final answer. You cannot simplify it anymore. But what do you observe over here is, unlike the previous example where all the, just by changing the plus to dots and dots to plus and the variable to its complement and vice versa, it's not always that the answer is in that way. So here, since the expression was not in the canonical form, we got the complement in some other pattern. Now we are going to simplify the Boolean expressions using Boolean laws. Let us take the first example, a very simple one. P dashed Q plus P Q dashed plus P dashed Q dashed. Now from these two terms, I can take P dashed common, and I will be left with Q plus Q dashed, and this is the other term. Now we know that Q plus Q dashed is equals to 1. So whenever we are simplifying Boolean expressions using some law, we have to mention the law, which law we are using. So that is P dashed plus P Q dashed. There's another law which states that A plus A dashed B is equals to A plus B. Now in this case, A is P dashed, A dashed is P double dashed, which means P, and B is Q dashed. So A plus B will be P dashed plus Q dashed. So this is P dashed plus Q dashed. This is your answer. Let us take another example. A dashed BC plus A dashed B dashed C plus A dashed B dashed C dashed. Now when you have such terms, you have to see that if you have any term, any variable, you can take common from more than one term. So I can see from these two terms, I can take A dashed B dashed common. Okay, so I will keep this unchanged for the while, and I will take A dashed B dashed common. So I am left with C plus C dashed. Now using this, putting C plus C dashed is equals to 1, I get A dashed BC plus A dashed B dashed, and this is 1. Now again, from these two terms, from these two terms you see a dashed is common, so I can get BC plus B dashed. If we write this a little other way round, am I not getting this again? That A plus A dashed B is equals to A plus B, where in this case this is A and this is B, so I can get A dashed into B dashed plus C, which is equals to A dashed B dashed plus A dashed C. So you can claim this to be the simplified expression of the question. Number 3, simplify A plus C into AD plus AD dashed plus AC plus C. So from these two terms, if I take A common, I will take, now this simplification can also vary from one student to another, but not too much. Okay, it should not be. Now see over here also I could have taken C common, but I just missed out. I'll do it in the next step, no problem. Now see, D plus D dashed is 1, so this remains 1, and over here you can take C common. C common, that means A plus 1 or 1 plus A is the same thing. Okay, so now this becomes A dot A plus AC, and this is C because 1 plus A is equals to 1, so this is 1. Now A dot A is equals to A, so this is A plus AC plus C. Again, if I take A common, then I will get 1 plus C again over here and C here. Again 1 plus C will be 1 using the same law, A plus C, which is your answer. Question number 4. Prove C plus BC whole dashed is equals to 1. So let us start with the LHS. C plus BC whole dashed. So using De Morgan's law, what do you get? B dot C BC whole dashed will be equals to B dashed plus C dashed. So C plus B dashed plus C dashed. Now C plus C dashed is 1, 1 plus B. C plus C dashed is equals to 1. Again this is equals to 1 because 1 plus B is equals to 1. So which is equals to RHS, hence proved. So in this way, if you have the Boolean laws at your fingertips, then you can simplify any Boolean expression without any hiccups. I will, at the end of this video, I will be adding some homework for you, which I expect you all to do it on your own and mail them. Now that we know how to simplify Boolean expressions using the laws, we will prove some propositional logics using Boolean laws. That is, this is only required when you are asked to infer anything or draw any conclusions using algebraic method. First, let us do one this will be question number 5. Prove A dot A implies B imply B is equals to 1. Now if you prove any expression is equals to 1, it means that this expression is a tautology. This is the algebraic form of proving tautologies. If it is a truth table, then only this expression you will be required to see that all the output column, all the critical rows have a 1, all combinations have a 1. But in algebraic method you have to prove that this expression is equals to 1. Now if you try to recall, you'll see that A implies B is equals to A dashed plus B. Now if you try to recall, then final. Now if you try to recall, you will know that A implies B is equals to A dashed plus B. This is the mathematical interpretation of the implication. So let's start with the LHS. A dot A implies B implying B. So one by one I'm going to open the expression. For this one, first I'll write A dashed plus B, and I will keep this in this form. So it's basically, this is the antecedent and this is the consequent. So if I use distribution law over here, A dot A dashed plus AB implying B. A dot A dashed is equals to 0. So here I have used the distribution law. And here I'm using the property of the complement, that A dot A dashed is equals to 0. So this is 0 plus AB implying B, which is AB implying B. Now again, if we use this, this is the antecedent and this is the consequent, it should be AB dashed plus B. So again, using De Morgan's law over here, the second law, which states that the complement of product is sum of individual complements plus B. Now B plus B dashed is equals to 1. This is the complementary law. That B plus B dashed is equals to 1. So A dashed plus 1, again by properties of 1 plus anything will be 1. Here I am using the property of 1, that A dashed plus 1 is equals to 0. Now see, there are different ways in which I have written the laws in every step. Somehow you have to express which law you have used in the steps. That's the objective. So in this way you have proved that this is a tautology. You can also do it to a truth table for your own assurance, that you'll see that the final column will have all ones. Now we are going to do a different kind of a problem where we have to conclude that if A implies B and B implies C, then it always infers A implies C. This is also known as the chain rule, but you have to prove this algebraically. Now when you have to prove it algebraically, these two are the premises whose product gives you the antecedent, and inferring this is the conclusion or the consequent, and you have to prove that the product of the two premises implies the conclusion is 1, which is a tautology. So we've taken the LHS first. So LHS is A implies B and B implies C implies A implies C. The brackets are optional, is equals to 1. Now we know that P implying Q mathematically means P dashed plus Q. So I'm going to apply that rule over here. A implying B will become A dashed plus B, and B implying C will become B dashed plus C. Whole thing implying again A dashed plus A implying C means A dashed plus C. Now here what I'm going to do is, instead of expanding this, I'm going to take this as the antecedent and this as the consequent and apply this law again. So that will give me a dashed plus b dot b dashed plus c whole dashed. So this is p now and this is q. So that is p dashed plus q is this. Now let us use De Morgan's law over here. Here I am using De Morgan's law, where this is the product of two terms and we are going to find out the complement. So this will be the sum of the individual complements. So a dashed plus b whole dashed plus b dashed plus c whole dashed plus a dashed plus c. So here we don't have anything to do, so I'll keep it over here, we will need it later. Now again I'm going to, this is the first law that I have used here, that second law, a dot b whole dashed is equals to a dashed plus b dashed. Here I will be using the first law, again De Morgan's law, but the first one, that a plus b whole dashed is equals to a dashed dot b dashed. So it's a double dashed means a, so that's complementary law. A double dashed is a dot b plus b dashed plus b double dashed means b dot c dashed plus a dashed plus c. Now if you open the brackets, you will see that a dot b dashed plus a dashed will form a useful pair, and over here b dot c dashed plus c will give you another useful pair. Now again we will be using that distribution law, that I'll write in terms of x plus x dashed y is equals to x plus y. Now in this case x is a dash. See, this is the term which is single, so that will be the single term will be x. So this is a dashed and x dashed is obviously a and y is b dashed, so the answer will be a dashed plus b dashed. Similarly over here, so single term is x, so this is c, x dashed is c dashed, and this one is b, so this one will be c plus b. Now a dashed plus c plus b dash together will give you 1. So that is a dashed plus c plus 1. Again c plus 1 is equals to 1, so that is a dashed plus 1 which is equals to 1. So proved. So that means the chain rule is a valid rule. Now suppose you don't get a 1 over here, then what does it imply? It implies that from these premises this conclusion cannot be drawn. In the homework I will give you an example like that you have to verify whether you can infer the consequent from the premises or not. Try it yourself, you might find it interesting.